All right, our fans, we're back for part 2. Just when you thought you were done, right? We actually need to talk about regression. So part 1 of the video was really just sort of giving you some introductory tools that you're hopefully going to use all the time when you use R. So now we're going to get specific into the tools that you'll use a lot for regression. So I'm just going to make this a little bit bigger. Give myself some space here. And I'm going to drop in a few more R chunks because we're going to need a bunch of these. All right, so now we're going to talk about regression. And we're going to go back here to our skim, our nice skim summary, and talk briefly about the variables themselves. So remember, regression is it's a highly flexible method, but essentially what we're doing in regression is we are predicting an outcome variable. In this case, a relatively continuous variable based on a set of input variables or predictors. It's very much like the equation for a line, y equals mx plus b, or y equals beta 0 plus beta 1x plus error. And so the idea is we're sort of fitting a line of best fit through that fits through the points in our data, at least when we're dealing with two variables at once, one y and one x. So what I want to show you here is an example that's closely tied to the readings. So you're going to read the Schrader article, which talks about a review of linear regression, and they use this food consumption data set, which I think is not too bad of an example. It's not education directly, but there are a lot of things I think that you can map onto this. In education, we have lots of things that are sort of continuous, and we have things that are binary, which is the other type of variable, categorical variable that we're looking at for this particular measure. So the first thing we want to do, let's say we are researchers who are really interested in food consumption, and that's going to be our outcome variable, our y. And we're interested particularly in the relationship between family income and food consumption. So what happens as families bring in more or less family income? What happens to the money that they spend on food consumption? Do they spend more or less on food? And I think you could probably predict, just using kind of thinking about how a house works, what the relationships might be here. But the idea here is to play with an example that we can kind of wrap our heads around and then try to extend it to some more fancy stuff. So let's start here with a very basic regression, and let's ask this question, and I can put this here and give it a heading if we want using the pound sign. Start with a simple linear regression. Does income predict food consumption? And the first thing I'm going to do is give this regression a name. So I'm going to call this food reg 1 because I'm going to want to come back to this later. And then I use the assignment operator to tell R that I want to save this for later. And now the command for the actual linear model is lm. It's very simple, linear model. And then in parentheses, and look, you get a nice little sort of prompt here from Stata, R, because R knows that this is a command that gets used a lot. So the first thing you want to put is your formula, and you start with your outcome, so food consumption. And then the tilde sign, which is the little wavy line that's underneath the escape. You might have to hold down the shift key. That's the tilde. So the tilde goes in between your outcome and your predictors. So y, food consumption, as a function of x. In this case, we're just going to look at family income. Okay, then we need to put a comma. The only other thing we need to tell R is what the data are, or where the data are. So the data in this case are in food.clean. Not food, remember, food.clean. And put that there. And then, so I can run this if I want. And you'll notice I have a new object up here in the environment called foodreg1. That's actually my model. It's saved in a bunch of lists. But if I actually want to see it, I need to ask for a summary of foodreg1. So summary is a good kind of general command for getting model information out of R and into the console here. So here I get a summary of the model. First thing you get is what's called a call, and that's the actual code that was included. So that's handy to remind yourself what the model was. Then you get the residuals. So this is basically a summary statistic of your residuals. Ideally, we want these residuals to be more or less normally distributed with a mean value around 0. So here we're going from about minus 5,000, and this is in dollars because that's what our food consumption is measured in, to positive 7,000. So it's a little bit skewed. And our median is at negative $48. So ideally, it would be right at 0, but that's not too bad. Then we get our coefficients. These are our model estimates. The first thing we get is our intercept. So that is beta 0 in our equation, y equals beta 0 plus beta 1 times x plus e for error. So that intercept is 4.155 e plus O3. Wow, that's kind of annoying. That's actually in what's called scientific notation. So what that means is if this sign is positive, we start here at the decimal point and we move it 1, 2, 3 points to the right. You might remember that from middle school algebra, maybe, going back quite a ways, I know. So so this number is actually about 4,155. And that represents the average food expenditures for a family with a family income of 0 in this case. That's because the intercept is the value of y, the predicted value of y, our outcome, when your predictors are equal to 0. So we would expect a family with no family income to spend about $4,000 a year on food. Now that seems kind of crazy. If you don't have any income, how are you spending on food? Maybe you're getting different kinds of support. Who knows? The model here doesn't know that. Remember, we're fitting a formula for a line. And so basically that line has to cross the x-axis at some point. And so that's the point of best fit. So that's our intercept. And here is the coefficient for our slope. And it is a negative scientific notation. Oh, geez. So we start here, we move 1 this way, and then another one, so that's a 0. So it's actually 0.06. The slope for family income here is 0.06. What does that mean? Okay, in general terms, a coefficient estimate or a slope estimate in regression tells us the amount that our outcome is predicted to increase when our predictor increases by 1 unit. 1 unit. I'll say that again. So a slope coefficient tells us the amount that our outcome is predicted to increase or decrease if it's negative if the predictor increases by 1 unit. So it's important to know, you can tell already, it's important to know the units of this stuff, right? So here, family income is measured in dollars. So a 1 unit increase in family income would be a $1 increase in family income. So as family income increases by $1, we would predict that the amount spent on food consumption, which is our outcome, would increase by about $0.06. And that's pretty handy, right? We know there are 100 cents in a dollar, so food consumption would increase by about 6 cents for every dollar increase in family income. All right, so that's how it works. Here we get a standard error for each of these estimates. And we get a t-value, and this is just the estimate divided by the standard error. And the general rule is the t-value needs to be above 2 in order to be or below -2 to reach statistical significance. And both of these are highly statistically significant. So these are both very, very small p-values. And these are p-values. They're kind of spelled out this way in R, but these are p-values. So this is 0.000005, and this one is 0.09 times and then 2. So these are both highly significant coefficients. So yeah, we can say that family income is related to food consumption and positively related. Down here we get our significance codes. These are nice, and these are sort of pretty standard. So we have 3 stars here is associated with 0.001 significance, so that's high significance. 2 stars is 0.01, 1 star is 0.05, and a decimal point is 0.1, or sort of borderline significance. And then we get what's called the residual standard error. So this is another measure of model fit. Ideally, we would want this to drop as we added predictors. I don't generally look at that as much. For me, I really like to look at the adjusted R-squared or the multiple R-squared, but adjusted is really better. So this is equal to 0.56. So what this means is that family income as a predictor explains about 56% of the variability in food consumption. So that's pretty big. Over half of the variability in food consumption here is explained by the amount of income a family makes. Alrighty, so that was a sort of a slow dive, but I really wanted to make sure we understood all the components that go into the output. Many of these will actually be very similar when we get to multi-level modeling. They'll look a little different, but in terms of interpreting coefficients, that's not going to change. You're going to be interpreting coefficients a lot this semester, so there will be estimates, there will be p-values, significance codes, and that kind of thing. Okay, so that is a simple linear regression. We have one y, one x variable. Let's ask a little bit more complicated question. So I'm going to paste it right here again with a pound sign. So what about kids? So what happens? We see here that family income matters. So if you have more family income, you spend more on food. Sure, that makes sense. But that model ignores the fact that some people have kids. And man, kids love to eat, right? I can think about my nephews. They go like gangbusters through a bag of chips or something else, right? They're voracious eaters. And so we haven't accounted for this in our model. We haven't seen if having kids in the family changes the outcome. But we have data on that. We know how many children are in the household. So let's run another model here. And what I'm going to do is I'm just going to copy my code from the first model. I do this a lot, and I'm just going to tweak it because the format is very much the same. So I'm going to call this foodreg2, and I'm going to, again, be fitting a linear model for food consumption. And here, so here's my outcome, and here are my predictors on the other side of the tilde. So I have family income. Now I just use a plus sign. It's kind of an additive thing. So plus, and then I just drop in my new variable, which is num children. And I can just grab that from my skim up above. So now I have two predictors. This is a multiple linear regression. And again, my data are still food.clean. And then I just need to change this summary to foodreg1, or from foodreg1 to foodreg2, so I get my updated summary here. And I can run this, and voila. I'm always amazed how fast software runs regression, because it's doing so much, and it just kind of crunches right through. Kind of fun. Okay, so here's our new model. So here we've added the dynamic of number of children. And so this is reflected in the call. The call has one additional variable. We get slightly different residuals. Not hugely different, but slightly different. The median changes a little bit, but again, it doesn't look too bad. Here's really where the excitement is, and that's in the coefficients. These are the things we want to interpret. So My intercept here has changed. It's gone from, let's see, $8,000 up here, or no, $4,000 up here to about $3,000 up here in this second model. So why does the intercept change? Is that a big deal? Well, no, it's actually not that big of a deal. But the reason it changes is because the intercept is totally dependent upon what other variables are in the model. Because again, the intercept is the value of y, the predicted value of your outcome, when all your other predictors are equal to 0. So before, we only had one variable, family income, but now we have two. So we have family income and number of kids. And so this 3,000 number, 2.963, this is the predicted value of food consumption for a family that has 0 income and has 0 children. So this is, if you think about it, if children add to the food consumption, right, this is about as low in food consumption as you can get. 0 family income, 0 children. And so that's why it changes quite a bit. Family income, on the other hand, doesn't change much at all. It is 0.05 instead of 0.06, and it's still highly significant. So now, after controlling for the number of children in the family, a $1 increase in family income translates to about a 5-cent increase in spending on food. And how about those kiddos? Are they expensive for food? You betcha, they are pricey. So here, again, this is significant. The p-value here is 0.02, so it's a little bit closer to our typical 0.05 cutoff. But number of children is here is significant. So it's, let's see, 8.25 times 10 to the second. So we got to move this 2 places to the right. Holy cow. Okay, so for each additional child in the family, we would expect to spend about $826 per year on food. And that's a biggie. Another thing we like to notice, again, I like to look here at the adjusted R squared. It's 0.6 in this equation, and it's 0.56 in the first equation. So the only difference between food reg 2 and food reg 1 is this number of children variable. And so adding number of children has explained an additional 4% of the variation. Not that big, right? Family income got 56%. Number of kids gets us another 4%. It's not huge, but it's still definitely something that is significant and is of worth note. Okay, so we've accounted for kids. We've accounted for family income. What happens when we decide to think about the garden? So this is an interesting question. So what about the garden? We have this variable that tells us basically whether or not the families that we sampled own a garden. And we have 2 values. We have yes and no. And this is basically what's called a dummy variable because it takes on only 2 values. This is also sometimes called a binary variable. That would be if yes was coded as 1 and 0 was coded as, or no was coded as 0. But they essentially mean the same thing. So we here in the first 2 variables we've included, we were able to control for family income and number of children. Those were continuous. This is a categorical variable. But we can control for this also in a regression model really easily. So again, I love shortcuts. I'm just going to copy the code from the previous model and paste it below. And this is going to be food reg 3. And now I'm going to add in, I have food consumption, family income, number of children, plus have garden FAC, I think is what it's called. Right? Let me look at the top. Have garden FAC. Yep, that's the number of the variable. And the cool thing about R is R already knows that this is a factor variable because I coded it like that up above. So it's going to handle it really smoothly and easily in the model with no trouble. I don't have to note anything in the formula. It already knows what kind of variable is there. And then I just want to ask for a summary of food reg 3. So let's see. Any bets on whether a garden makes an impact? Dun dun dun. It does not. Sigh. I still think they're pretty cool, but unfortunately, it looks like after you've controlled for family income and number of children, whether or not you have a garden does not have an impact on what you spend on food consumption. And looking here at the adjusted R squared, it actually went down. So we were at 0.6, and now we're at 0.595. So this is a good example. This is why I prefer adjusted R squared to regular R squared. By definition, regular R squared increases as you add in any variable to a regression model. It could be a highly related variable. It could be a totally unrelated variable. It doesn't matter. It's going to increase. And so, in other words, regular R squared, this multiple R squared, doesn't correct for garbage. And you always want to correct for garbage in your models. You want to adjust for variables that aren't doing a very good job. And so that's what happened here. Our R squared value actually went down because this poor garden variable was not doing very much. And so it adjusted the predictive power down a little bit. Okay, so garden doesn't do anything. Now let's run one more model here that gets really fancy. Are you ready? I hope so. So let's talk about possibly studying whether or not variables can be moderators or interactions with other variables. So I describe this a little bit more in the handout. So if you want my not off the cuff explanation of this, I have that in the actual handout for this week. So long story short, regular regression is what we call additive. And so what that means is when we control for other variables in the model, we basically hold them constant. And we assume that the presence of one variable in the model does not impact other variables' relationships with the outcome. So to give you an example, we're looking at family income here and number of children. And we see this, this estimate of about 0.05 or 5 cents. So for each additional dollar that you earn, your family earns in income, you're expected to spend about 5 cents more on food. Well, the way this model works, we are assuming that that relationship holds whether your family makes $1 in family income or whether your family makes $100,000 or $10,000, so on and so forth. We assume that it's sort of monotonic, that it's just sort of increasing. And we also assume, since there are other variables in the model, that the number of children does not change that relationship. So maybe if you have 4 kids, for example, that fundamentally changes the number of things that you have to spend on, and you end up spending a smaller fraction of your family income on food. You have to be really tight with your budget and kind of stretch things. And so that's something that would be important to look for, but that you don't always test unless you explicitly test a moderator or interaction analysis. And so that's what we're going to do here. We're going to test whether or not there's an interaction between the number of children in your family and family income. So to do that, I'm again not going to reinvent the wheel. I'm just going to copy this. And I'm going to call this Food Reg 4 because that's my 4th regression. And then, so the first 3 are fine. I have family income, food consumption is my outcome, family income, number of children, have garden, plus, to specify an interaction, you put one variable in a colon and then a second variable, like this. Ta-da, just like that. So now I have a main effect for family income, a main effect for number of children, a main effect for having a garden, and then an interaction effect between family income and number of children. So the software is going to create that interaction effect, and it's going to test it statistically, and we can see whether or not it's realistic to assume that these things should be considered separately or if they should be considered as interacting with one another. So we run that, we get our results. Let's see, family income, number of children, yep, have garden. Oh, I see. So in the example, I didn't include garden here. So I'm noticing that my estimates are different from the handout. So I'll drop garden out. That's probably a good idea because we're seeing here that garden was not significantly related. So we probably should take that out. So for food reg 4, I'm just going to drop garden and just include the significant stuff. There we go. That looks a little bit better. So now when we look at this, so the key is when you test an interaction effect, and this comes up a bit in the, I believe it's the article by Lauren Schutte or Schutte. I'm not actually sure how to pronounce her last name. A scholar at UT Austin. The recommended reading for this week was the piece on intersectionality and critical theory using quantitative methods. And one of the key approaches to examining intersectionality quantitatively is by using interaction effects. And so this is a good example of what that looks like. This is how you actually include an interaction effect and you test it. But one problem with these is they are notoriously not very powerful. So main variable effects are hard to detect sometimes, while interaction effects can often be even harder to detect. So here we have an estimate here, but the p-value here is non-significant. So if it was significant, we could start to think about, what might be going on there. How are things shifting in ways that would change the impact. One way to think about this, to interpret this, as the number of children increase, the slope on family income for each additional child is predicted to go down by about let's see, three this way, 1, 2, 3, by about 0.008. So about a penny or less. So as if this were significant, that would mean that as families have more children, that relationship between income and food gets smaller. It's not as strong. It goes from 0.06 to 0.05 to 0.04. And probably because, more kids just imposes lots of additional types of expenses. And so you really kind of have to stretch your budget with food in ways that you might not be expected to before if you don't have kids. So, okay, so that is a moderator analysis or an interaction effect. And the last thing I'm going to show you how to do is how to use the Stargazer package, which is super cool. Let's see if I can paste this in here. So I love this part about R because it is so easy to summarize your results. So what you can do, first you want to load up the Stargazer package. So I'm going to type library and then Stargazer. And there it popped up, so I have it on my machine. If you don't, of course, you can, and you get a little cite there, you can, Merrick is asking for some citations, and you can put that in a paper. It's considered good form to cite the authors of our packages. Of course, if you need to install it, you can install it over here. And so once Stargazer is up and running, now I'm going to just copy and paste this table because it's going to take me a while to actually type this one out. So I'm going to create a summary table. This is a new object, and it's going to use the Stargazer function, which creates really nice tables. And basically what summary table does is it collapses multiple regression models together into a publication quality type summary. And so I want to include in my summary food reg 1, food reg 2, 3, and 4. Those are the 4 models that I ran. And notice they're separated by commas. Type equals text, so this is going to pop out a table in text format right below. You can change the font size if you want. I have it at normal. You can make it smaller, larger. I only want 2 digits on my decimal point. I think that's APA, but of course you can adjust that. And I only want to see, in addition to my estimates, I want to see the N, the sample size, R squared, and adjusted R squared for each model. I can also specify my star cutoffs for what's significant. So I have 0.05, 0.01, 0.001. You could add another one there. You could make 0.0001 if you wanted. And then the last thing, this is a super cool trick. If you add this command out, it will create an HTML table for you that you can copy and paste into Word or into, I think, Google Drive, but definitely into Word. So I'll show you. And the name of this thing is going to be test.html. And it's going to go right into whatever your working directory is. So my working directory, well, I better double check. So this is week 2. So I'm just going to say set this as my working directory just because I want to be able to find that thing when it's done. Okay, so that's all you need to do. And then you just click run. And you get a few formatting errors, but nothing too serious. And then look at that, folks. You get a really nice looking summary of all 4 regression models. So here's model 1, where family income was by itself. Here's model 2, family income and number of kids. 3, income, kids, and garden. 4, income, kids, and the interaction between the two. The standard errors are in parentheses. The number of observations, R squared, and adjusted R squared, and you even get the little key right here too. So this is just a really nice way to summarize all the models. And if you look, hopefully, let me update this. Click the refresh button. I should have somewhere, there it is, test.html. So I can click this, and I want to open it in a web browser. Ooh, yeah, so let me see if I can bring this over and show you what this looks like in my web browser here. So coming across, beep, beep, beep. So here, in my web browser, I now have a really nicely formatted table that I can just copy like this, or do select all if you want, and copy and paste into Microsoft Word. And Microsoft Word is going to recognize this so you can clean up the names. But the hardest part, getting the values in there, is just done for you, which is so cool. I can't stress that enough. So it's pretty exciting. Love the Stargazer package. You can do the same thing with descriptive statistics too. So, okay. Well, that ended up being a nice video. Hopefully you enjoyed it. You found it helpful. And that's where we are. So we started with a simple linear regression. We added variables to create a multiple linear regression. We added continuous variables like number of children. We added categorical variables like have a garden. And then we even tested a moderator or interaction effect to see how that worked too. And then we wrapped it all up by using the Stargazer package to create a super cool summary. So hopefully that made some sense, and let me know. If not, I'm happy to answer any questions. Good luck.